Swayam Prabha. Digital India. Educated India.
Welcome to the 10th lecture on the time series modeling and forecasting. In the last lecture, we have discussed how the property of stationarity is important, why a time series has to be stationary. If the time series is stationary, then we can investigate the properties of the probability mechanism generating it, but only the stationarity of the process is not enough. There is one more property which plays very important role, and that property is ergodicity. A time series should be ergodic along with stationary, so that we can investigate the properties of the process in a proper way. Now, we define an ergodic process. Before giving the proper definition of the process, first we consider an example. Now, suppose we have a process y t which is defined as y t equal to mu plus x plus u t. Now, u t is a Gaussian white noise process. It has mean 0 and variance 1, and x follows a Bernoulli distribution which has the probability mass function p x equal to 1 upon 2 if x is equal to minus 1 or plus 1, otherwise it is 0. Now, expectation of x is 0. And what is variance of x? It takes two values, minus 1 and 1. So, minus 1 square into 1 by 2 plus 1 square into 1 by 2. So, you get 1. Then the variance of y t, before that expectation of y t is mu, because expectation of x is 0, expectation of u t is 0. So, expectation of y t is mu, and variance of y t is equal to variance of x plus variance of u t. Now, variance of x is 1, variance of u t is 1. So, variance of y t is equal to 2. For the k equal to 1 to so on, the autocovariance function of the process is gamma k is equal to expectation of y t minus mu y t plus k minus mu, and then this is equal to expectation of x plus u t into x plus u t plus k, and then this is equal to 1, because expectation of x square is equal to 1, expectation of u t x is 0, expectation of x u t plus 1 is 0, and expectation of u t plus 1 is equal to 0 for k greater than or equal to 1, and variance of the process is 2. So, rho k is equal to 1 upon 2. So, the process is second order stationary. The process is stationary and it achieves statistical equilibrium also. But then the problem is that the process revolves around -1 plus mu or 1 plus mu, depending upon the initial value of x. If the initial value of x is 1, then the process revolves around 1 plus mu. And if the initial value of x is -1, then the process revolves around -1 plus mu. So, although the process achieves statistical equilibrium, the equilibrium state is not unique. So, the process is actually not ergodic. You also observe that ACF of the process is constant. So, increasing lag does not have any impact on the autocovariance function of the process. It remains constant. Or you can say the effect of past observations does not diminish with lag as time increases. The process revolves around either -1 or 1 depending upon the initial value of x. Now, x can take value either -1 or +1. So, ultimately y t is equal to either -1 plus u t for all t greater than or equal to 2, or it is 1 plus u t for t greater than or equal to 2. Depending upon the initial value of the x. If the initial value of x is -1, then the process revolves around -1, and if the initial value of x is +1, then the process revolves around +1. So, although the process achieves statistical equilibrium, this statistical equilibrium state is not unique. One more thing you must notice that rho k is equal to 1 by 2 for all k. It means the autocorrelation function is constant 1 upon 2 for all k. What does it mean? Or what does it imply? It implies that the effect of any observation sustains for a long period. It does not vanish. Because as you are proceeding, the correlation coefficient rho k remains constant. So, the correlation coefficient between y1 and y2 or y1 and y3 or y1 and y4, these all correlation coefficients are the same. So, y4 has the same effect of y1 as y3 has or as y2 has. So, this is the problem. Now, suppose y1, y2, yn is an observed time series and y bar is equal to 1 upon n summation yt. So, y bar is the mean. Then you can easily verify that mu is unbiasedly estimated by y bar. Ultimately, expectation of yt is equal to, we go to this slide, mu. So, if you take expectation of y bar, then you get mu. So, y bar unbiasedly estimates mu. So, there is no problem with the unbiasedness, but y bar converges either to -1 plus mu if the value of x is -1, or it converges to 1 plus mu if the initial value of x is +1. In some sense, you can say that the process has two different origins from where it can start, or you can also say that the process gets stuck away from the data generating process mean. The data generating process mean is mu, but the process gets stuck either around -1 plus mu or 1 plus mu. So, it leads to inconsistent estimator. So, if you are observing the time series y1, y2, yn, and if you try to estimate the mean mu using these observations, and you use sample mean as an estimate of the population mean or the mean of the distribution mu, then y bar is an unbiased estimator, but y bar either converges to -1 plus mu or converges to 1 plus mu, depending upon the initial value of x, whether initial value is -1 or +1. That is why your estimator, though it is unbiased, but it is inconsistent estimator. Further, I mentioned earlier also, rho k is constant and does not diminish as k tends to infinity. It means the strength of dependence on first observation remains intact with increasing t. It does not diminish. So, if you are observing a single time series, then on the basis of a single time series, you cannot consistently estimate mu. That is the problem. Now, you can understand why ergodicity matters. With the property of stationarity, it ensures the statistical equilibrium, but it does not ensure that your equilibrium is unique. Ergodicity along with stationarity ensures that such an equilibrium is unique. So, this is very important. As you have seen in the last example, if the statistical equilibrium is not unique, then you face problem in, say, estimating the parameters of the process on the basis of a single realization or single time series. Then algoticity tells us that a single long time series becomes representative of the whole data generating process, just like a large IID sample becomes representative of the whole population or distribution. Now, this is very important. In time series analysis, what you are doing? You are observing a single time series. So, it is very important that your time series is a proper representative of the entire data generating process. Just like the IID sample, which represents the probability distribution from where it has been generated. The properties of the algorithmic process can be investigated on the basis of a single long enough observed time series. If the process is not algorithmic, then you will face problem. Algorithmic processes forget the past in long run, means far apart terms are distributed independently of each other. Now, notice that in the last example, when you obtain rho k, the value of rho k is equal to half for all k. So, with increasing k, the value of rho k does not diminish. So, any dependence on the initial observation remains intact. Or you can say the process does not forget about the past in the long run. But with the algorithmic process, this property holds, means the algorithmic processes forget the past in the long run. Now, this is the proper definition of algorithmic process. A process y t, t belongs to capital T, is set to satisfy algorithmic property with respect to a bounded function f, if for the realization y t, t equal to 1 to so on, the sample average 1 upon n summation t equal to 1 to n, f y t converges almost everywhere as n tends to infinity. And if the process is stationary also, then expectation of f y t is equal to mu for all t, and in that case 1 upon n summation t equal to 1 to n, f y t converges to mu, means expectation of f y t. So, this condition gives you the property of algoritmicity for any bounded function f, and for this realization, this is the sample average 1 upon n summation t equal to 1 to n f y t. Then if the process is algorithmic, then for any bounded function f, this sample average converges almost everywhere as n tends to infinity, and if the process is stationary also, then this converges to mu, where mu is expectation of f y t. One more thing, a time series has to be stationary in order to be algorithmic. So, it must satisfy the stationarity. As a special case, a data generating process is mean algorithmic if limit n tending to infinity, expectation of 1 upon n summation t equal to 1 to n y t minus mu whole square is equal to 0. It means the mean of the time series 1 upon n summation t equal to 1 to n y t. This is the sample mean. This sample mean converges to mu almost everywhere. Similarly, a data generating process is variance ergodic if limit n tending to infinity, expectation of 1 upon n summation t equal to 1 to n y t minus mu square minus sigma square whole square tends to is equal to 0. So, this is the condition for variance ergodicity. Similarly, the data generating process is autocovariance ergodic if the sample autocovariance converge in mean squared error to the true parameter, that is, if limit n tending to infinity, expectation of 1 upon n summation t equal to 1 to n y t minus mu y t plus k minus mu minus gamma k whole square is equal to 0. Now, this is the sample autocovariance. So, a process which is ergodic in mean and autocovariance means a process which is ergodic in first two moments is also called ergodic in wide sense. Now, we consider some more examples and check whether those examples satisfy the property of ergodicity or not, and what are the implications if the property of ergodicity is not satisfied. Now, suppose you have two fair tetrahedrons 1 and 2. The sides of tetrahedron 1 are marked -3, -1, 1, 3, and the sides of tetrahedron 2 are marked -4, -2, 2, 4. Then one of the tetrahedron is selected randomly and its independent throws are performed. Means initially what you have done? You have selected either tetrahedron 1 or 2 with equal probabilities. You have assigned probability half to tetrahedron 1 and half to 2, and then you have selected one of the two tetrahedrons, and then you start throwing that tetrahedron and you perform independent throws, and then you get a process y t. You can easily verify that the process is second order stationary. In fact, the process is strictly stationary. The reason is that different throws are independent, and the process is going to achieve statistical equilibrium. So, there is no problem, no issue with the stationarity. Now, you can easily verify, you easily check whether the process is mean ergodic or not, or variance ergodic or not. Now, suppose you select tetrahedron 1, then what is the expected value of y t if 1 is selected. Given that initially you have selected tetrahedron 1, what is the expected value of y t? It is equal to 0, minus 3 into 1 by 4 plus minus 1 into 1 by 4 plus 1 into 1 by 4 plus 3 into 1 by 4. So, this is 0. Expectation of y t given 2, this is also 0. And if you calculate expectation of y t, initially you have selected either tetrahedron 1 or tetrahedron 2. So, this is also 0. So, there is no problem with the mean, the process is mean algorithmic. Now, you can calculate the variance of the process, and then you can check whether the process is variance algorithmic or not. Okay. Expectation of y t square if 1 is selected. Y t can take 4 possible values, minus 3, minus 1, 1 and 3. So, you have 3 square plus 1 square plus 1 square plus 3 square. So, 20 upon 4 equal to 5, and expectation of y t square given 2 is equal to 10. So, the process is mean algorithmic, but it is not variance algorithmic. The variance either converges to 5 if initially you have selected tetrahedron 1, and the variance converges to 10 if initially you have selected tetrahedron 2. So, the process is not variance algorithmic. We take another example. Suppose x follows a Poisson distribution and ZTs are IID, each having mean theta minus mu and variance sigma square z. Then we define the process y t as y t equal to x plus z t. Then what is expectation of y t? Expectation of y t is equal to expectation of x, and expectation of x is mu plus expectation of z t, which is theta minus mu. So, you get theta here. Then variance of y t. Now, variance of y t is equal to variance of x plus variance of z t, because x and y are independently distributed. Now, variance of x is mu and variance of z t is sigma square z. Again you can easily obtain gamma k, which is equal to expectation of y t plus k minus expectation of y t into expectation of y t plus k, which so you have theta square. And then you substitute the values of y t and y t plus k. Y t is equal to x plus z t, x plus z t plus k minus theta square. Now, this is equal to expectation of x square, which is mu plus mu square. Cross product terms are 0 and expectation of z t plus k is also 0. So, gamma k is a constant. The process is second order stationary. In fact, the process is strictly stationary also. But the process is not mean ergodic. Why? Because if x 1 is the initial selected value of x, then mean of the selected sample revolves around theta plus x 1 minus mu. Means the initial value of x is say x 1. And you can see that after that the value of x does not change. So, it remains x 1. So, after initial value y t is equal to x 1 plus z t for t greater than or equal to 2, if x is equal to x 1. So, the process starts revolving around x 1 plus expectation of z t, which is theta minus mu. Now, this is the problem. Although the process is stationary, but it is not mean ergodic. So, ergodicity is a problem with this process. Ergodicity is not just the characteristic of the process. It also depends upon the manner in which the experiment is conducted to collect the observed time series. So, it is not just the characteristic of the process, but it also depends upon how the experiment is performed or how the data is collected. These two things also affect the ergodicity of the time series. For example, while conducting a study about the air pollution, suppose the data is collected daily on the level of nitrogen dioxide in air at a particular time. So, what we have done, we have initially selected a time of the day. Say suppose initially we decided that we are going to collect the sample at 8 a.m. and then daily we start collecting sample at 8 a.m. Now, the time series which we are going to obtain is not a true representative of the process, the air pollution. It is actually representative of air pollution at 8 a.m. What we are doing? Initially, we have decided that we are going to take observation at 8 a.m. and suppose we have selected this particular time randomly. So, we are not biased, but once we have decided, we have unbiasedly decided that we are going to collect sample at 8 a.m. We stick with that time, means daily we collect data at 8 a.m. Then your resulting time series will give you information about the air pollution at 8 a.m. It is not the representative of air pollution of the day. So, this ergodicity or the resulting time series is not ergodic. It is not a true representative of the characteristic which is our main focus or which we want to study, the air pollution of the day. So, ergodicity is not just a problem with the process, it is also a problem in the manner the experiment is conducted or the observations are collected. So, the same example, on the first day the time of measuring nitrogen dioxide level randomly and then decided, and then daily the data is collected at the same time. Then inference drawn will be severely affected by the timing selected on the first day, and resulting time series won't satisfy ergodic property. So, while collecting the data, one has to be very careful. He is interested, the person is interested in some particular characteristic, and then he collected the time series thinking that his time series is a true representative of the characteristic which he wants to study, but that may not be true. So, that is why the property of ergodicity is very important. Just like the random sample, the IID random sample from a population, your time series has to be a proper representative of the population or proper representative of the process which has generated it. Remember, you are observing just one time series from the process, means at each time point you are taking just one observation. In air pollution example, you are taking sample at a particular time only. So, you have to be very careful since you are collecting data only one observation at each time point. You have to be very careful that your time series is a proper representative of the probability mechanism of the process which has generated it. Otherwise, it is going to lead to wrong inferences. You may be interested in something and you are getting something else. Now, we define orthogonal projection. Now, suppose y t is a time series and the process is a covariance stationary process, and we write p y t plus h given y t minus 1, y t minus 2, so on y t minus n equal to beta naught n plus beta 1 n y t minus 1, so on plus beta n n y t minus n. So, p is a random variable such that the coefficients beta naught n, beta 1 n, so on beta n n, these coefficients are obtained by minimizing this quantity S, which is equal to expectation of y t plus h minus beta naught n minus beta 1 n y t minus 1, so on minus beta n n y t minus n square. So, it is just like the regression problem. In some sense, this is the regression of y t plus h on the values previous observation previous values of y t minus 1, so on y t minus n, and then you are minimizing this expected mean squared error. Then p y t plus h given y t minus 1, so on y t minus n is called the orthogonal projection of y t plus h on y t minus 1, so on y t minus n. And it actually gives you the predicted value of y t plus h given y t minus 1, so on y t minus n. And in this orthogonal projection, suppose you take limit n tending to infinity, then the orthogonal projection of y t plus h on y t minus 1, y t minus 2, so on all past values is defined as p y t plus h given y t minus 1, y t minus 2, so on equal to limit n tending to infinity p y t given y t minus 1, y t minus 2, so on y t minus n. A covariance stationary process y t is called linearly deterministic if p y t given y t minus 1, so on is equal to y t. So, if this orthogonal projection is equal to y t, then we say that the process is a deterministic process. For a stationary deterministic process y t can be predicted correctly using the entire past y t minus 1, y t minus 2, so on. And one step ahead prediction error becomes 0. But it does not mean that y t is a constant or it is a non-random variable. Now, we define the backward shift operator which is defined as b y t equal to y t minus 1 and b k y t is equal to y t minus k. Now, we define purely non-deterministic process. If all deterministic components of a time series have been subtracted in advance, then it is called a purely non-deterministic process. Okay, now we consider some examples and we check whether those processes are deterministic or non-deterministic. The first example is, suppose y t is a process defined as y t equal to a cos t plus b sin t, and a and b are independently distributed standard normal random variables. Now, suppose you take y t plus y t minus 2, then y t is equal to a cos t plus b sin t. So, you get a cos t plus b sin t plus a cos t minus 2 plus b sin t minus 2. Now, we collect the terms involving a. So, you get a cos t plus cos t minus 2 plus b sin t plus sin t minus 2. Now, we make use of the result that cos a plus cos b is equal to 2 cos a plus b by 2 into sin a minus b by 2. Similarly, sin a plus sin b is equal to 2 sin a plus b by 2 cos a minus b by 2. We make use of these two results, and then you can easily obtain that the first term is equal to a 2 times cos t minus 1 cos 1, and second term is b 2 sin t minus 1 cos 1. Then you take 2 cos 1 outside and inside you obtain, after taking 2 cos a common, you get within bracket a cos t minus 1 plus b sin t minus 1, and then a cos t minus 1 plus b sin t minus 1 is equal to y t minus 1. Or you can also write 2 cos 1 as sin 2 upon sin 1, or from here you obtain y t equal to sin 2 upon sin 1 y t minus 1 minus y t minus 2. So, given y t minus 1 and y t minus 2, you can predict the value of y t without any error accurately. Or p y t given y t minus 1, y t minus 2 so on is equal to sin 2 upon sin 1 y t minus 1 minus y t minus 2, and this is equal to y t. So, projected value or the predicted value is same as y t, there is no error. So, this process is a deterministic process. The process is a deterministic process, but it does not mean that it is a non-random process, it is a random process. Now, we consider another example. we consider the process y t equal to summation j equal to 1 to k r j cos omega t plus theta j, and theta j follows a uniform distribution over the interval 0 to 2 pi. Then you take y t plus y t minus 2, which is equal to summation j equal to 1 to k r j, you take common, and then you have cos omega t plus theta j plus cos omega t minus 2 plus theta j. Again we make use of the result that cos A plus cos B is equal to 2 cos A plus B by 2 cos A minus B by 2. Then you obtain 2 times cos omega, you can take outside the summation sign, and inside you obtain summation j equal to 1 to k r j cos omega j t minus 1 plus theta j. So, again this is the same process, except that in place of t you have t minus 1. So, you write it equal to y t minus 1. So, y t plus y t minus 2 is equal to 2 cos omega y t minus 1, or y t is equal to 2 cos omega y t minus 1 minus y t minus 2. So, p y t given y t minus 1 y t minus 2 so on is equal to 2 cos omega y t minus 1 minus y t minus 2, which is equal to y t. So, again y t is a deterministic process. Now, we consider one more example. Suppose y t is equal to a plus b t, where a and b are random variables, a follows normal 0 1, b follows normal 0 1, and since a and b are random variables, y t also is also a random variable. Now, you can write y t minus 1 equal to a plus b t minus 1, y t minus 2 is equal to a plus b t minus 2. You multiply y t minus 1 by 2 and subtract y t minus 2 from that. Then you obtain, you are multiplying this by 2 minus this. So, you get a plus b into 2 t minus 2 minus t plus 2. So, you get b t. So, this is equal to y t, or y t is equal to 2 y t minus 1 minus y t minus 2. Again p y t given y t minus 1 y t minus 2 so on, this is equal to 2 y t minus 1 minus y t minus 2, which is equal to y t. Again the process is a deterministic process. So, if a process is a deterministic process, it does not mean that it is not a random process. In all these examples, you have observed that y t is a random variable, it is a random process, but it is a deterministic process. So, today we have seen two important properties of the time series processes. One is ergodicity. You can compare ergodicity with the consistency property of the IID random variables or IID sample. A process has to be ergodic so that the time series observed from the process is a true representative of the probability mechanism which has generated it, and then it helps you to estimate the parameters of the process properly or to investigate the properties of the process properly if it is ergodic. If the process is not ergodic, then what happens? It may be stationary, you may be able to find unbiased estimators of the parameters, but those unbiased estimators or your entire process, you can say, revolves around or it stabilizes around 2 or maybe 3 or 4 different positions. So, this is the problem if your process is not ergodic. So, I stop here. Thank you.
Hello and welcome to this piece of literary snippet. Perhaps the most popular literary genre after novel is the short story. Sharp, compact narratives whose charm lies not only in what is said, but also in what remains unsaid. Today I will be reading one of the shortest instances of a short story that I have ever encountered, and indeed the very charm of this particular story that I am going to read out today lies in the way it abruptly ends. It is an ancient tale from Mesopotamia which has been retold by several authors, among whom the name of Somerset Maugham stands out. The adaptation that I will be reading out is perhaps the closest to the one that Maugham wrote. The story is titled, in all of its adaptations almost, as Appointment in Samarra. Here is the story. A merchant in Baghdad once sent one of his servants to the market. The servant was supposed to buy provisions for the merchant, but when he returned, he came back empty-handed. Indeed, the servant had all gone white, and trembling with fear, he told his master that he had met death in the marketplace. When I entered the market, the servant said to his master, I was jostled by a woman, and when I turned to look at her, I saw that she was death. I am very scared, master, because death looked at me with a threatening gesture. Can you please lend me your horse so that I can fly away from Baghdad to the town of Samarra and thereby escape death? The master, being a good man, gave his servant his best horse and saw him gallop off to Samarra to escape death. Then the master himself went to the marketplace and confronted death. Why did you make a threatening gesture to my servant? Asked the master to death. And death replied, it was not a threatening gesture. Rather, it was a start of surprise. I was astonished to see your servant here today, because this evening I have an appointment with him in Samara. See you in the next episode of Literary Snippet.